This is an AS Maths differentiation question which is being applied to modelling. A lorry is driven between London and Newcastle. In a simple model, the cost of the journey, C pounds, when the lorry is driven at a steady speed of V kilometers per hour is cost C is equal to 1,500 over V, the steady speed, plus 2V, the steady speed again, over 11 plus 60. So part A, we need to find, according to this model, in the first part of part A, the value of V that minimizes the cost of the journey. Now, anytime you get a question and you've got a function and you want to find its minimum or maximum, then we want to differentiate. Another option would be to complete the square, but that's only useful if we've got a quadratic, and we don't have a quadratic here. So we're going to differentiate C to get dc dv, which we'll write in a moment. But the first thing I'm going to do is to write this in a form that makes it easier to differentiate. So rather than 1500 over v, I'm going to write 1500 v to the power negative 1. Then the second term I'll write as 2 over 11 and then put the v to the side, plus 60. When we differentiate, it's going to be dc dv. It's important that we get the letters correct. The letter at the top is always the subject of the equation. The letter at the bottom is always the letter that we're differentiating. So we multiply by the power, then subtract 1 from the power. So I'll have negative 1,500 v to the power negative 2. And then the 2 over 11v just becomes 2 over 11, and the 60 will disappear. Now, at this maximum or minimum, in this question it's a minimum, it could be a maximum, we don't know yet, maybe we need to prove that later on. We know that dc dv will be equal to 0. In other words, there's a gradient of 0 at the turning point of the graph of this function here, and we're going to locate that turning point. We're assuming at the moment that it's a minimum. So dc dv we make equal to 0. That means that we're going to have negative 1,500. Now I'm going to write this again as like this, over v squared plus 2 over 11 is equal to 0. Let's rearrange it now because we want to solve for v. So I'll write 1,500 over v squared is equal to 2 over 11. If I sort of just rearrange it, then what I'll do is do the reciprocal of both sides. So I'll have v squared over 1,500 is equal to 11 over 2. From here I can work out what v squared is. So v squared is going to be 11 over 2, and then what we're going to do is we're going to times that by 1,500, and that gives us a value of 8250. And then v is a speed, it'll just be the positive square root of that. So square root of that number will give us 5 root 330. Okay, I guess we could give the speed like that. It's kilometers per hour. So kilometers per hour. Now we could also write this answer as a decimal, and I would go for 3 significant figures. So we could write it instead as 90.8 kilometers per hour. And I'll just write down that this is an answer that's been rounded to 3 significant figures. Now we'll move on to the second part of part A, and we need to find, according to the model, the minimum cost of the journey. So we are going to take the exact speed and we are going to put it back into the original cost equation here. So part 2, the cost is going to be 1,500 over the exact velocity, speed, sorry, which is the 5 root 330. Don't use your rounded answers. We only want to round right at the very end. Plus 2 times 5 root 330 over 11 plus 60. So let's work that out and see what we get. Now I do get an exact answer, but this cost we want to give in pounds and pence. So what I get on my calculator is 93.02891 and so on. So since it's a cost, we want to give that in pounds and pence. So we'll have £93 and 3 pence as our cost here. So there's our answer to the second part of part A, and our answer for the first part of part A is given here, either exact or two free significant figures. Part B. Prove by using d squared c over dv squared, that's the second derivative, that the cost is minimized at the speed found in part A1. So we want to prove that it's minimized. The speed that we found in part A1 was 5 root 330, the exact speed. And at a minimum, we're expecting that d squared c over dv squared, the second derivative, is greater than 0. So its value is always the opposite. At a minimum, this should be greater than 0. At a maximum, it will be less than 0. So I'm just going to state that. So at minimum, the second derivative d squared c over dv squared is going to be greater than 0. Now how do we do that? We're going to differentiate a second time. We're going to substitute in v and we should get a positive number. So let's do that. So the second derivative, let's find our first derivative. Now where was it? It was up here. There's our first derivative. We want to differentiate that a second time. So remember, multiply by the power, take one away from the power. So I need to multiply negative 1500 by negative 2. So that will give me 3000 v to the power negative 3. We take one away from the power. And then the 2 over 11 disappears. So we're just left with this here. So now what we do, we're going to sub in v equal to 5 root 330. So now the second derivative is going to become, and I'm going to write this as 3000 over v cubed. It's the same as this, and that will be 5 root 330. There's my v, and that is going to be cubed. Okay, let's see what this value is. Now I get a small number. I get 4 basically times by 10 to the power of negative 3. Okay, but it's still positive. It's greater than 0. It doesn't matter how small it is, it's greater than 0. So we conclude that since the second derivative is greater than 0, therefore the value of v found is a minimum. And lastly, part C, state one limitation of this model. Okay, so there's lots of different reasons we can pick. I've just picked a couple. Probably the most obvious one is that a lorry may not travel at a constant speed. This model assumes that it's being driven at a steady speed. It's going to speed up, it's going to slow down, there's going to be traffic, all those types of things. And the other reason that I thought of is that costs may vary with speed. When vehicles travel at different speeds, their fuel consumption changes, and it may be that if this lorry is driving above a certain speed, its fuel consumption is going to increase, which means the cost may be higher than given in this model, or if it's driven at a slower speed, that may decrease its fuel consumption. So again, this is another reason that we can give, as long as you give something that's sensible and related to the model, related to velocity and cost. I'm sure that would be an acceptable answer.